Hello everyone, hi and welcome you all on this lecture number 34 of Mathematical Physics series, and the topic which we were studying was the generalized function or distribution. So in lecture number 33 we have studied some basic functions like what is a signum function or what are the step function and so on and so forth. But before I continue this video, first let me do a slight correction to one of the question that I did in the previous question. Actually, the question was correct, just some minute correction. So I have done a question which was plot this function theta of tan hyperbolic of x. Okay, so this was the question. So I wrote this question. This will be 1 when tan hyperbolic x is greater than 0, and this function will be 0 when tan hyperbolic x is less than 0. So this is by definition. So what? How the plot should look like? So if this is my this theta of tan hyperbolic of x and this is x, so for this region, for this whole region, tan hyperbolic is positive, so it will give me a value +1, and for this region the tan hyperbolic is negative, so it will give me the value 0. So instead of this plot in the video, I have plotted something like this, +1 and -1. So it was a slightly correction, although I have written this clearly that theta is defined as this, but if you lose some a little bit of focus or concentration, so these minor mistakes happen. So please correct this. This is not -1, this should be 0 and +1. Okay. So this was a slight correction to the previous video, although I have given this correction in the description box as well as in pinned comment. So if anyone have forgot to see that, so just make a correction. Okay. So now let's study the lecture number 34 by continuing the previous topic. So the topic which we will study will be Dirac delta function. Okay, so for this video, we will be mostly focusing upon some basic concepts. The first is what are the other mathematical representation of a delta function other than its definition. Okay, and we will be looking at some particular distributions, some particular functions and some limits like box function, Gaussian function, Lorentzians, and some others also. And we will see some of its properties and what is the relation between this delta function and this other, the two functions which we have studied in the previous videos. And we will solve some questions if time permits, and in the next video we will be having some more properties of this delta function, and that will be useful in quantum mechanics and as well as in mathematics to solve some problems. Okay, so shuru karte hain our discussion on mathematical representation of this Dirac delta function. So the first function which we will study in this representation is a very simple function, which is the box function. Okay, this function we call box function, and it is defined. Let's a function is represented by f of x, and this is defined as it has a value 1 by 2 sigma for this range when x is in between these two particular limits, that is, let's suppose a minus sigma and a plus sigma. तो इन दो values के बीच में function की value कितनी होगी 1 by 2 sigma. For all other cases the value of the function will be 0 otherwise. Okay, but there is a key point in this function. We will keep the area under the box function to be unity. So area under box function we will keep to be area under box function is 1. So it means that if this is the height, is this 1 by 2 sigma represents the height of this function, then what will be the width of this function? Then the width of the function will be 2 times sigma, so that the area is 1. So now let's have look at a plot like how this function will look like. So suppose this is our xy coordinate system. So this is our x coordinate and this is our y coordinate, which represents the value of this function fx. Okay, so let's suppose the value of a is somewhat over here, and we have two values, that is a plus sigma and we have one value, this is a minus sigma. So the value of this function, this box function, between this limit is some finite quantity which is the value is 1 by 2 sigma. Okay, 1 by 2 sigma. And rest at all other points, the value of the function is 0. So it has two discontinuities, one at a minus sigma and one at a plus sigma. So this box function have two discontinuities, one at this point, a minus sigma, and one at this point, this is a plus sigma. Okay, so what will be the width of this function? As we have discussed, the width of the function will be 2 sigma, so that this area under the curve should be 1. So this area is 1 unit. So what are the limits in which this particular box function will represent a delta function? So let us discuss some limits. See, we have two, area is constant, we can't change that. So we have two parameters, one is width and one is the height. But are these both parameters, the width and height, are independent? The answer is no, because if you change the height, since the area is constant, one of the other parameter will change. So what is the limit? So if we change the sigma, let's suppose this represents some, it's in both the quantity, so we cannot say the sigma. So let's suppose the width is 2 sigma. If we decrease the width, if this width goes to 0, since the area is conserved, then the height will go to, height is 1 by 2 sigma, this quantity will go to infinity or very high value, so that the product of these two functions, that the width and the height will remains the same, that is 1. And this happens because area is 1 unit. Okay, so this is, so in this particular limit, when the width goes to 0 or the height goes to infinity, this box function is similar to the delta function. So we can say in this particular way that this function, this box function fx, this is 1 by 2 sigma, this function goes to delta function in a limit when this limit is taken to be sigma tends to 0. So this width 2 sigma tends to 0 or sigma tends to 0, these are roughly the same or the same thing. So if you take that limit sigma tends to 0, this is the box function. This is an approximate representation of this delta function. This is x minus a, because this 1 by 2 sigma was defined in this. So this function should be defined between between x. This is in between a minus sigma to a plus sigma. So when sigma goes to 0, this box function goes to delta function. Okay, and this is 0 otherwise. So this is the one way to represent a delta function, or uh, this is the one way to represent delta function. But अब हमारे पास एक दूसरा question है. We have another question like, is this the only function which in particular limit shows us a similar behavior of a delta function? Then the answer is no, because there may be as many functions as you can think, and those functions in some particular limit which will represent this delta function. Then what should be the properties of such functions that represents a delta function in some particular limits? So let us briefly write some of the properties, and we will see some more examples which represents the delta function. So first point which we can say is, there is many functions, or we can say infinite such functions or sequences exist in that goes to delta function in particular limit. So we can say uh, that infinite number of such functions or sequences exist, infinite number of such functions or sequences exist that tends to delta function in particular limit, in particular limit. Okay, so now our next question is, what should be the properties of these functions? तो ऐसे बहुत से हजारों, मतलब इन्फिनिट नंबर ऑफ फंक्शंस पॉसिबल हैं जिनसे डेल्टा फंक्शन जो किसी पर्टिकुलर लिमिट में डेल्टा फंक्शंस की तरह एग्जिस्ट बिहेव करेंगे, तो उन functions की properties क्या होगी? Okay, so let's discuss the properties of this function. So let's suppose we write the function in this particular form. So this function is phi. Let's write a parameter a. This function is a parameter of a, which we will take the limit, and this function is defined at x minus x naught. So what properties this function should have? Uh, it should has a peak at x naught. इस function के पास एक peak होनी चाहिए x naught पे. That should be symmetric about this point. This function should be symmetric about the point x naught. This okay, and the first or not the first. This third thing should be integrable function. So what a integrable function is, if we integrate this function between this limit, so if we integrate this, that should give me 1. Okay, this is basically the normalization condition. So this is all if this particular, these three particular criterias a function follow, then we may say, well, it is not necessary, but it may happen that that function in some particular limit goes to delta function. So the idea is very simple, that if we change this parameter a, as a goes to 0, or we can say a decreases, we can say as a decreases, since the area under this function is unity, the height of that function will increase. If a decreases, since area is constant, so the height height की spelling गलत हो गई, let me correct it. So the height of that function will increase. So this is a kind of behavior which these kinds of function will represent at some particular point x naught, and in particular these particular limits. So what we can write in a very compact form, that this function phi of a, which is a function of x minus x naught, if these properties are followed, and if we take a limit a goes to 0, then this function will represent a delta function at x naught. So this is quite understandable how this can happen. Okay, now let's show you some examples of this function phi a, which has these particular kind of properties, and which really goes to delta function in those particular limits. And here I will give you some homework also for you, or kar lena wo homework. So the first and the very common function is a Gaussian function. So how the Gaussian function is defined? Let's say a function of x which has some parameter, let's say a. तो जो function defined है इसकी value आएगी 1/2 under root of pi into a is some constant, some parameter, exponential e raised to power minus x square by 4 times a. So this is a representation of a Gaussian function, and how this function will look like. This function will look like something like this. Okay, let me correct. Since these functions are symmetric, so you should be very careful about these functions, because when you read StatMech, okay, or statistical mechanics in some advanced statistical mechanics course in your master's program, then you will realize that even a small symmetry can give us a very peculiar, strange behaviors. Okay, so that's why you should be very careful about this function. At this stage you don't need to worry about it. So this is our origin, so this is x is equal to 0, so this function is symmetric about the origin, uh, about this point x is equal to x naught. How do I know that? Suppose this exponential is a form of some exponential function of minus x minus a whole square, x minus, let's say, b whole square divided by 4a. So this function is symmetric about x is equal to b. So this x minus something, so this function is the mean value. So this x, so this is x minus mu whole square divided by 4a minus into exponential. So this mu represents the mean value. So what is the mean value over here? So this is 0, or the average value. Okay, average value of this function. So this is 0. So here it is b, here it is mu. So you should remember, if I write this function, okay, let me just write another function and ask you a following question. Suppose I write this, let me use this color. So this is phi of a into x is 1 by 2 under root pi into a exponential of minus x minus mu by 4 pi into 4 times a. So this some basic properties of this function. This function has a peak at mu. ओके इस फंक्शन का जो पीक होगा वो म्यू पे होगा. एक्चुअली दिस a, so here it is some standard deviation or the width of this function came, so this width is proportional to a. Okay, this is proportional to a, proportional to a. This width is proportional to a, and this is called the variance. So let me write the exact form of this Gaussian distribution, and then you can relate these quantities with that exact form. Okay, so this is exact form of this Gaussian function. So the Gaussian function look like this. Suppose I represent by gx. So this is my Gaussian function. So this is 1 by sigma square root of 2 pi. This is exponential of minus half x minus mu by sigma whole square. So this is the exact representation of an Gaussian function. So this mu is the mean. Here you can see this sigma square will come, this square and the sigma square will come out. So this sigma square is the called the variance of this Gaussian function, and you can see the sigma square root of the sigma squares come over here. So only this particular unit power of the sigma come over here. Okay, so this you can relate this from here, like this a square. Okay, so this is a, so you should have a square root of a over here. So this a is proportional to this variance, and this variance is proportional to the width. So this is the exact representation of this Gaussian function. You can read more about it from any places, and it's good to know some properties of this Gaussian function. So if you take this particular limit, if you take this limit, a goes to 0, a goes to 0 means that you are decreasing the width of this Gaussian function. So this, in this particular limit, this function pi over a exponential of minus x square by 4a will tend to a delta of function x, because its mean at 0, so the delta function will have a peak at 0. If this was the function, if I write, so if a goes to 0, 1 by 2 under root pi over a exponential of minus x minus mu whole square by 4a, then this function will tend to delta of x minus mu. It means that this Gaussian function will have a peak at the position mu. Okay, in this particular limit. So this is one particular example in which this, when a goes to 0 at the width or the variance goes to 0 of this Gaussian function, that will represent a delta function. So this is one particular example. There is another function that is called the Lorentzian. Okay, so this another function is called the Lorentzian. Okay. So what is a mathematical expression? So this is phi a of x. So you can write it as a divided by pi a square plus x square, this function. Okay, let me write it again because something messed up. So this was a divided by pi x square plus a square. So this function is the Lorentzian function, and this function will also go to this delta function in this particular limit if this a divided by pi x square plus a square. So this function will go to delta function. So I'm giving you, assigning you some homework. So the first homework is to plot this function. plot this function. You can use any graphics tool to plot this function. Just you should have an image how the Lorentzian function look like. Okay, so you can use Desmos or uh, any other calculator will just show you the graphs of this particular function. Okay, so you have Lorentzian, you know how the Lorentzian function look like. Now the second thing is to plot this function. The first is Lorentzian, you should plot the Lorentzian, and second is you should plot this Gaussian function, and take the same value of a, and second check uh, which function goes, which function has a, or in a very simple way, which function decays faster. So your next question is which function decays faster. कौन सा फंक्शन इसमें पहले डिके कर जाएगा, इधर मींस जब a goes to 0 which function will reach 0 faster. Okay, so this you should comment below. और ये बस 2 मिनट का काम है कि आप बस दोनों को प्लॉट कर लो, सेम a की वैल्यू ले लो, जस्ट टेक द लिमिट a goes to 0 and see which function goes to 0. And this one thing कि Lorentzian goes to 0 or the Gaussian function will decay faster will help you in many places. If you do this uh, complex analysis course in your master's course, then you will realize how important this concept is, that which function goes to 0 faster, the Lorentzian or the Gaussian. So I'm not only giving you an idea about this delta function, but also preparing for your master's classes. Okay, so this is a kind of view which I have, that I should not only let you prepare for your competitive exams, but also make you so strong that you can easily grasp the thing in your masters. Okay, so this is the whole idea of this platform physics of this. So now I am assigning you some homeworks to do, and if you do it honestly, real believe me, one day sooner or later you will realize that how important these ideas or concepts are. I know at this stage of time you will realize अरे क्या करा रहे हैं यार, कुछ भी होमवर्क दे देते हैं करने के लिए, but believe me, do these functions. So मेरा जो next function है, this is 1 by 2a exponential of minus mod x by a. प्लॉट करो इस फंक्शन को, you will see a sharp peak like this, इस तरीके से. Okay, so here at this point there will be a sharp peak, sharp peak होगी. Okay, and this kind of functions will come in your when you solve this potential v is minus delta x in quantum mechanics. When you solve this kind of potential in your quantum mechanics, then these the solution is something with then the solution of this Schrodinger equation with this delta function will have a wave function which has a sharp peak like this. Okay, so this wave functions came from there, and you can also check that this is symmetric and all the properties follow. And if you do this limit a goes to 0, this function will also go to delta function. So some homework, plot this function and verify this properties. कहाँ गई? Verify these three properties. In this particular example, these three properties follows. You just calculate the area under these curves and see whether this is one or not. The fourth example which I wish to give is check this in limit, which is let's say a goes to 0. So this is sine x by a divided by pi into x. This also goes to delta function. Okay, so this you should verify. And the fifth example, देखो fifth example हम लोग कर चुके हैं. I have given, okay, I will tell you later. Okay, so let's check this function when limit a goes to 0, 1 by 2a sec hyperbolic square x by a. This also goes to delta function. Okay, so this is your homework. So what are the homeworks? The first is plot this using any graphics tool, any graphics tool, or the simple one is use this Desmos application, which is very great. And the second is verify the properties. Verify the properties mentioned above. Okay, so वो जो properties हैं उनको चेक कर लो. But यहाँ पे एक चीज आप देखो, हम लोगों ने एक फंक्शन देखा था that was tan hyperbolic of let's say x by a. Tan hyperbolic x by a ये फंक्शन कैसा था? This was a signum function in limit. When limit this a goes to 0, this function became signum function. इसका अगर जरा डेरिवेटिव लो d by dx तो वो क्या आ जाएगा? इसका tan hyperbolic का डेरिवेटिव क्या होता है? 1 by a. This is sec hyperbolic square x by a. So you can see this. Okay. So again, we have a question that if we take the derivative of this signum function with respect to some parameter, then there must be a relation, because this represents in this limit when a goes to 0, this represents a delta function, but sure, there is a factor of 2. So there must be a relation between signum function and delta function, and that must be related with some derivatives. Okay. So this we will see in a few minutes, but before that, let me tell you one other mathematical representation, which is some related with some Fourier transform. Either I have not told you anything about the Fourier transform, but those who know, it's very good. And let's just read one property about this delta function and the Fourier transform. Okay, so this is our topic. So this is a kind of other mathematical representation of a delta function in terms of Fourier transform. So this function is represented like this. So delta function at x is defined as 1 by 2 pi. This देखो ये जो representation है that depends upon how you define the Fourier transform. Okay, so this is not the only one way to define this delta function in terms of Fourier transform, but this is the one way. So delta function is defined as 1 by 2 pi. This is integration of minus infinity to infinity. This is dk e raised to power I k x. So somewhere in some books you will find this factor to be square root of 1 by 2 pi, or you will find it 1 by 2 pi. It just depends how you define the Fourier function or the Fourier transform. Okay, so this delta function, so this is the inverse Fourier transform of a constant, और यहाँ पे जो constant है उसकी value कितनी है? 1. So this is okay, not this, this delta x is inverse Fourier transform of a constant, and here the constant is unity. Here constant is unity, or you can simply say 1. Okay, here the constant is 1. So if you take an inverse Fourier transform of a constant, and if that constant is 1, so this will give you a delta function. So this represents this e raised to power I kx simply represents the plane wave. So in a k space, this plane wave has a value from minus infinity to infinity. So this is k space, or the some other space. So in this other space, this function has a value from minus infinity to infinity. But if you come to real space, that is x space, that function turns out to be a delta function, and it has a value which is a sharp peak at some point, and here the peak will be at 0. So here is a very important concept in mathematical physics, that if a function is extended in one particular space, then in its Fourier transform it should be contracted. Okay, so अगर x डायरेक्शन में सपोज करो हमारा कोई एक फंक्शन है जो कि x स्पेस में एक्सटेंडेड है, बहुत दूर, मतलब उसके बहुत दूर, मतलब सपोज करो प्लस माइनस इन्फिनिटी तक उसकी वैल्यूज डिफाइंड है, तो उसका जो Fourier ट्रांसफॉर्म होगा वो बहुत ही शार्प मिलेगा. फॉर एग्जांपल दिस, इफ यू टेक अ प्लेन वेव, so this is extended from minus infinity to infinity, but its Fourier transform or the inverse Fourier transform is a delta function which has a sharp peak at zero value. Okay, so this is a very good concept and very important. So what it is, I'm stating it again. So if a function is extended, as long as you can think, so if a function is extended in one particular space, then in its Fourier space that function will be very contracted. So आई होप यू गेट द पॉइंट कि एक स्पेस में अगर उसका एक्सटेंशन है तो इन अदर Fourier space it should be contracted. Okay, so this is a very good idea and the concept, and you will realize this in your master's course. Okay, so if you uh, so this is one mathematical representation, or you can take this delta of x minus a. So this is delta of x minus a, or you can, since this is a symmetric function, so you can write delta of a minus x. So this is 1 by 2 pi integration of minus infinity to infinity dk e raised to power plus minus ik of x minus a. So this plus minus, this is valid for both the signs, either you take the plus or the minus, but this should be case a should be a real value, or the value of a should be real. Okay, so this is the relation between the Fourier transform and the delta function, and they are related with each other. So one is the delta function is the inverse Fourier transform of a constant, and that constant is unity. Or if you take the Fourier transform of a delta function, so that will come to be unity. So here it is an important point that you can write is that the Fourier transform of unity is, sorry, Fourier transform of delta function is unity. Fourier transform of delta function is unity. And one other important point that you can think, that the Fourier transform, this is not related with this delta function, but since I mentioned Fourier transform, so let me just tell you, Fourier transform of a Gaussian function, Fourier transform of a Gaussian function is a Gaussian function. So so if this is in X space, then this is in K space, then both the nature of the both the functions will be same, and the nature will not change. So if one is Gaussian, then the other one is Gaussian. But in delta case, if in one space it is delta, then the other space it should be a constant, that is unity. So let's use this delta function property and try to get some interesting results. And those results are very useful for your BSc coursework, or if you have done it, then it's very good. Or this the direct result can be asked in any particular exams, and based upon this result, you will solve many properties, which I will be giving you as a homework, because those things are not very important for your competitive purpose, but let's just do it. It will take hardly 1 or 2 minutes. So this is the case. So I can mathematically I can rewrite this. So this is the limit where g goes to infinity, and I can do this integration between minus g to g e raised to power I kx dx, and you can verify this. I can write this as 1 by 2 pi, this is limit g goes to infinity, this is e raised to power I kx divided by I x, sorry, I k, no, this is ikx. So I have, so this was dk, not the dx, so this was dk. So if I do the integration with respect to k, so I will get ix, but this is between the limit minus g to g. So if you put this limit, you will get a function of sine, because you know this sine x is defined as e raised to power ix plus e raised to power minus ix divided by 2I. So here is an I, and you will get a factor of 2. So you will overall get x 1 by pi x. This is limit g goes to infinity sine gx. Okay, so this is a function. Or you can simply write this limit, let's suppose g goes to 0, you can write sine x by g divided by pi over x. If you remember, and so this is the just so this is a function which I have just written some times ago. So this was the function. I will show you where I have written this function. So this question number 4. Okay, so you can see this represents the delta function. So here is the proof of this. Okay, this actually represents the delta function. Okay, okay, so next you can verify this quantity that, or already I have given you the homework that this minus integration to integration delta x dx give you 1. So that is the area under the curve. So you can simply write this is minus infinity to infinity limit g goes to infinity sine of gx divided by pi x. You will do the integration and verify that this value is 1. Okay, and it's very simple. You just do a substitution of these variables and just verify it, and you can get this results. Okay, but if you are honest and you are doing some practice, so just to take this as a homework, because these, see, आप ये नहीं कह सकते कि कब कौन सा क्वेश्चन किस एग्जाम में आ जाएगा. Because if you take, let's say, T.I.F.R written exam, the second written exam I'm talking about, so they can give you any question that they want. If they give some question of this particular type of delta function type, and you have not studied or you have not rigorously done these problems, so if they ask question based upon this delta function, then there will be a trouble, and you don't know what they will ask. Okay, and the question, and the second stage written of this GS or the T.I.F.R exam is totally subjective. You have to write each and every answer. Like, you don't just have to take the answer. You have to write. Okay, so every step they will check whether you are doing right or wrong, or what you are thinking about that particular question. So please do these questions honestly. It will, so learning never goes waste. So that's the key point, and do these questions. So what we have learned till through this discussion, that delta x can be represented as 1 by 2 pi integration of minus infinity to infinity I k x dk. So this is one. Or we have seen that delta x can be, from this particular definition, we have come to know that this limit when a goes to 0, sine of x by a divided by pi of x, this limit will also give me a delta function. So these were the two mathematical representation. But the meaning of the delta function, the physical meaning of the delta function, it's more clear when you include this delta function with some integrations and operate with some functions. Okay, so these are the abstract definition, but the meaning is more clear when you operate, or when you do an integration with some functions. Okay, so now let's do our basic question that we were more interested, that what is the relation between this delta function and this step function or the signum function. Okay, so let us take the relation between delta of x and theta of x. Theta of x is the step function. Okay, so we will justify this relation between by some examples. So we have seen this example. This is tan hyperbolic of x by a. So in the limit when it's a goes to 0, so this function represents signum function, and we have represented this was e of x, and we have defined what this function is. Okay, so if we take the derivative of this function with respect to x, which we have done earlier, so this will come out to be 1 by a sec hyperbolic square of x by a, and this will represent Dirac delta function, Dirac delta function in the limit when a goes to 0. Okay, so in both the limit, there should be a relation between the signum function and the Dirac delta function. So actually, there is a factor of 2 over here. Okay, so this function, so if you do the integration of minus infinity to infinity, so the area under the curve will be 2. So to make it normalize, there is a factor of 2. So what we can write is d by dx of this. this function e of x is nothing but 2 times of delta of x. So delta of function, so this whole function represents this delta function. If we put over here, this 2 will cancel out and this differentiation will be the exact. So this is the relation between the signum function and the delta function, that the derivative of the signum function will represent twice 2 into the Dirac delta function. So this is the one particular uh, expression or the relation. Now the second relation we were interested in about with the delta function and this heaviside step function. So we know what is the relation between this signum function and step function. So what that relation was, theta of x is nothing but half of 1 plus e of x. So you can verify this. If e of, let's suppose x is greater than 0, then e of x is plus 1. If x is less than 0, then e of x is minus 1. So in this case, if x is greater than 0, so this theta of x will be 1 and this will be 0. So we have a correct definition and the relation between this theta of x and this step function. Okay. So we are done. You just substitute with this e of x kind of thing and you will, so from here you will get this e of x as 2 times of this theta of x minus 1, and if you differentiate it you will get d by dx of theta of x is equal to delta of x. So now here is a concept. So what this function will, okay, so okay, let's state in a this way. This theta of x is a unit step function which has a finite discontinuity, and delta of x is a function which has an infinite discontinuity at that point. So if you have a function which has a finite discontinuity at any some point, you take a derivative of that function, so that finite discontinuity will turn out to be a delta function which has an infinite discontinuity. Okay, so here is a concept which you must remember. So let me write the concept over here, and this is very important. ये बहुत जगह पे आपको quantum mechanics में या mathematical physics में अभी हम लोग questions करेंगे and you will realize how important this is. The concept is, if a function, I will explain. Okay, if a function fx is discontinuous at x is equal to a, then the derivative of the function will be related to Dirac delta function. It means that this function has a sharp peak at x is equal to a. Let me explain in Hindi for some students कि अगर कोई फंक्शन जो कि डिसकंटिन्यूअस है x इज इक्वल टू a पे, अगर उस फंक्शन का आप डेरिवेटिव लोगे तो जहां पे डिसकंटिन्यूटी थी वहां पे एक डिराक डेल्टा फंक्शन से रिप्रेजेंटेशन होगा अगर आप उसका डेरिवेटिव लेते हो. ओके, so let us take a very simple example and let us understand this concept. Okay, so here is the example. Suppose my function is defined over this. So fx is 0 when x is less than a and it's some constant c when x is greater than a. So this is a function. So how this function will look like? Suppose, okay, let me draw it clearly. Suppose you have this as an x-axis and this, let's suppose this is your y-axis. Okay, so let me plot this function. So this function is 0 till this point a, and this function is some constant c from this point. Okay, so we have a sharp discontinuity over here, or amount of discontinuity kitni hai? C. The amount of discontinuity is c. So fx is discontinuous at x is equal to a. So if you take the derivative, if you plot this dfx by dx, then how this function will look like. So this is x and this is df by dx. So at this x is equal to a, there will be a sharp peak which goes to infinity mathematically, and this all the function will look like this. Okay, so if we have a discontinuous function, then its derivative will include a delta function. This is x minus a. Okay, and what is the strength of this delta function? C, because the amount of discontinuity here it was c. So it's better to represent that as c times delta of x minus a, where c is the strength of the Dirac delta function or the amount of discontinuity. And how this we calculate? This is the area under the Dirac, this df by dx curve. Okay, so this is a thing. So I will relate one example which we did one. Okay, so let's just do that particular example, and that example was, so my entropy, this is S versus temperature graph. So this is T and this is S versus T graph of the first order phase transition, and that was uh, let's suppose this is the entropy relation. So we have a first order phase transition. So this example I explained in the very first video, or the lecture number 32 or 33 I guess, where I stated about the step function and the signum function, and this is ice and this is water. So we have an entropy versus a rough diagram should look like this. Okay, it's come, let me draw it again. So this function will come like this, and here it will have a finite discontinuity, and this function will, then its function will increase further. So now the question was how the Cp or Cv, because these both functions are related with ds by dt, will plot look like. So if you take, this is a ds by dt, and this you take the temperature x is t, then there, so see here is a finite amount of discontinuity. So if you take the derivative of this function, so there must be a sharp peak which goes to infinity, or this is related by a delta function. So this was a question that was asked to me in this interview of ISC exam. Okay. So if you don't know this relation between how the discontinuity is related with the delta function, then probably you would not be able to answer. And believe me, I was not able to answer at that time because I don't know. So I was just able to explain why there is a discontinuity over here, because I have studied the first order phase transition. Then I know that ds by dt, or the specific heat of this constant pressure or volume, that is related by a delta function. I gave this explanation, but I don't know this mathematical tool, that this discontinuity, how this discontinuity is related with this delta function. And here will be some behavior, depends upon how this curve look like. So here you can plot accordingly. This is just the slope of ds by dt. Now let's look at some other examples. So here is my, so this session is already being 46 minutes, but it's good to have some question in mind. Okay, so I will do one more question, and then I will uh, discuss other things in the next video. Okay, so first one example and then one question. So first I will take an example. Suppose I have a function which look like this. Okay, so this is, let's suppose, my xy coordinate, and this is a function of fx. Let's take a very simple example which we have taken of a box function. So box function will have a discontinuity at these 2 points, which was a minus sigma. Let's suppose this is a, and this is at a plus sigma. So this function has a discontinuity at 2 points, that is a plus sigma and one is a minus sigma. So let me rescale this axis. Okay, this goes out of this recording room, but don't worry about that. So this is just a function. So we have this representation. Okay, so rest all other points, this function is 0. So now I want to plot this function with the same limit at, okay, so this is now my new axis x, and this function is dfx by dx. Okay, so one thing which is very important over here, the strength of the Dirac delta is positive or negative. So here this discontinuity is positive, and here when it falls down, the discontinuity is negative. So you should remember that at this point, a minus sigma and this point a plus sigma. The Dirac delta, this is related by Dirac delta function, but it will have an opposite strength. At this point, the Dirac delta will have a positive strength, and at this point, the Dirac delta will have a negative strength, because this discontinuity is positive and this discontinuity is negative. So this is another important aspect. Let's say this discontinuity is that was 1 by 2 sigma. Let's just write it as a constant c. Then you can represent this function dfx by dx as the delta function representation. So how you will write, this is c, this is the constant, this is the strength of the delta function. So this is the delta x minus a minus sigma. So it means you have a delta function at a minus sigma. At this is a minus sigma and this is a plus sigma. So you have a delta function at a minus sigma which has a positive strength, minus c times delta of x minus of a plus sigma. So it means you have another delta function which which has a peak at a plus sigma and which has a negative strength, that is minus c. So this is the mathematical representation of a derivative of a box function. Okay, so if you take a derivative of a box function, so that must be related with a delta functions. It's not very simple as you think. Okay, now let's do a question that was asked in T.I.F.R examination and see whatever we have studied, can you apply that concept here or not. Okay, so let me define this question. So this question was asked in T.I.F.R exam. So question is, your function is fx is very simple. It is the greatest integer function. E of this box represents greatest integer function. So those who don't know what is the greatest integer function, so it is mathematics. So I will explain by some examples. So suppose its value is 1.06. So this function will give you 1. Its value is 0.99. So this value will give you 0. So it means you have to write a function which is the greatest but the smallest than this number. Or more precise definition, you can look at some Wikipedia or some other sources, but let me first plot this function so that you can have a pictorial view of this function. Okay, so let me take this. Okay, so this is fine. So this is my x-axis and this is my y-axis where I will plot this function of e of it. So if I plot like this, if I this darken the bubble, so it means this function is included at that point. If I just leave it like that, it means that point is not included. Okay, so this function is represented like so. This 0 is included if I take till here. Okay, so this is point 1. Then I have a discontinuity. Then this point 1 is included when this is 1. Okay, then again we have a discontinuity. Okay, so this is 2 and this is 2, this is 3. So in bit, if we have a x value in between, so if we have a x value which is equal to or less than 3, then this function x will give you the value 2. Okay, so this is a kind of function how it is defined. So these are okay. So I will plot the discontinuities by white so that you can differentiate the function, and uh, this uh, this orange color is your function. Okay, so these points are included over here. So let me plot some negative also. So this look like this. Okay, so here it is discontinuity. So you can see in this function there are lot of discontinuities. So we have one discontinuity as 1, 1 at 2, 1 at 3, 1 at 4, and so on and so forth. And we have some negative uh, this x values also. So this will look like this. So if you see the and okay, so let me complete first. Let me complete the question. What was the question? So you have fx is defined at x like this. You have to find what is the value of this. Okay, as simple as that. So you have to find the value of this. Now first thing is this, you know how to deal with this discontinuities. Okay, so this is like this. So this has a positive discontinuity, positive discontinuity, positive, positive. So all the discontinuities are positive, so that we know from here. So if we plot this function, okay, if we plot this function x, so how this will look like? So this function will have a peak at x is equal to 0 due to this discontinuity. Then it will have a peak at x is equal to 1 with this discontinuity. Then it will have a peak at 2 with this and the strength of these functions are same, so it's my bad in plotting. So this is 3. So these all are delta functions at different places from minus infinity to infinity. So it's very simple to write dx by dx of fx, which is nothing but dx by dx of this x. How it is represented? This is represented at by delta functions x minus the position. The position कहाँ पे 0 1 2 3 4. So let me write an index n. Okay, so यहाँ पे इनका ये यहाँ पे delta functions होंगे, and let me put a summation sign n is equal to uh, minus infinity to infinity. N is equal to minus infinity to infinity. So this all points will include this delta function. So when n is negative, so this become positive. So these all points will be included there. When n is positive, these all points will be included here, and there will be a point when n becomes 0. So this delta function is represented by n becomes 0. So you can see, if you know what is the relation between this discontinuous function and this delta function, then this question you can easily do in this T.I.F.R exam if this is asked again. Okay. Okay, so it's a 55 or 56 minutes long session. So let me give you an idea what we will study in the next video. So in next particular video, I will give you another example which was asked in just exam. Some about this delta potential in quantum mechanics. I will give you some. It's examples. Okay, so we will do the examples and how that example second derivative is related with delta function. Some representation of delta function in different coordinate system, we will do that. Then we will come to the properties of the delta function, and we will study about I think 7 or 8 or 9 properties of this delta function, and then we will do some questions that was asked in just examination and some practice questions. Then we will do some integral. So you can see, still I have completed in 3 videos, but still there's a lot to learn about delta functions. So hopefully these videos are very helpful for you in order to understand physics and in order to understand this delta function and these difficult concepts, and this will help you to solve questions in competitive exams. Okay, so let's finish this discussion over here, and we will see you in the next video. Take care, bye bye, and keep learning. Thank you very much for watching this video, and please do those questions very rigorously and sincerely. मिलते हैं next video में.